On problem 1, there's a typo that should say Caroline is helping her younger sister Julie with her math homework. Julie was given the sequence 10, 50, 250, 1250, 650, and she writes the equation t of n equals 2 times 5 to the power of n and makes the graph it right. Caroline suddenly says, no, you're writing the wrong equation. The correct equation is t of n equals 10 times 5 to the power of n minus 1. It should be a minus 1. Is Caroline's equation correct? Is Julie's equation correct? So I'm going to copy that sequence and their equations down real quick. So you can do the same. Okay, sorry. So one equation is t of n equals 2 times 5 to the power of n. And the other equation is t of n equals 10 times 5 to the power of n minus 1. So we want to know what equation is correct to generate this sequence. So basically, if we look at this sequence, we can tell that it's multiplying by 5. I should have written some stuff down before this. I'll just kind of write it off to the side. And I said it. But a geometric sequence is repeated multiplication. So in this problem, we can tell that it's multiplying by 5. R is, and to figure out what it is, we do 50 divided by 10. This one's not too hard. We can tell just by looking at it, but some of them you will have to do division to figure out what that multiplier is. And R is going to be the variable that your book will use here. And then, so we want to know what equation's correct. We could do a couple of different things. We can plug in the terms to plug in 1, plug in 2, plug in 3 for n in both of these. But here, this 2 would be the 0th term if we work backwards and divide. And 5 is our multiplier. Where here, 10 is our first term. And 5 is also our multiplier, or R. So the benefit of this second equation, so if I plug in 1 here, 1 minus 1, I get 0 for my exponent. Remember, an exponent of 0 makes this become 1. So 10 times 1 gives us 10, and that's our first term. The benefit of this guy right here, writing your equation this way, is you don't have to find the 0th term. So by writing the n-1 as the exponent, you don't have to work backwards. And again, this one, it's not too hard to work backwards to divide by 5. And this, I'm kind of jumping ahead to part B here, sorry. It says, what are the advantages? So here we don't have to work backwards for the 0th term. And then on this one, just going underneath it, it's more simplified, I'll say, because we don't have the exponent with the subtraction in it. So both of these are the same. This is a lot of what we did in Math 1. This is often how we're going to write it in this class now. And then, so part C says T of n equals 18 times 3 to the power of n. Nope, just 3 to the power of n, not minus 1. And we want to rewrite it in the other form. So again, 18 is our 0th term and 3 is our multiplier when it's written this way. Sorry, I don't know why that's not focusing. Okay. So if I were to write out this sequence, again, I know 18 isn't part of the sequence, but if I take 18 and I multiply it by 3, I get 54. And then if I multiply by 3 again, I get 162, and so on. So this 18, remember that's our 0th term. We don't actually want it in our equation when we write it this way. When we write it this way, our equation uses the first term. So our first term here is 54. And it still uses the same multiplier, but our exponent is n-1. Okay. So 10-82, there's kind of a lot to, I'm going to share the book so we can read it. It says, with a record-setting lottery jackpot projected for noon tomorrow, Mr. Hanks is standing in a very long line to buy a ticket. The man behind him in line taps on his shoulder to ask, hey, have you thought about how you'd spend the money if you won? Before Mr. Hanks can answer, the woman in front interrupts and says, first, you have to decide whether you want to get your winnings in one lump sum right away or if you want to receive them spread out over time. I'm sure one option must be a better deal, but I haven't figured out which one. When Mr. Hanks gets home, he immediately goes online and learns that the lottery winners do have a choice, receiving the winnings in a single payment of 51% of the jackpot right away, or spreading payments of the jackpot over 20 years. He also learns that the jackpot is projected to be $50 million. He knows that if he takes a single payment, he can invest it right away and earn 4% annual interest on that money. If he chooses to receive the payout over 20 years, the lottery commission will invest the money for him. They guarantee to pay $1,500,000 in the first year and to increase the amount they pay by 5% each year. At lunchtime, Mr. Hanks walks into your class and asks for your help. If your team can figure out the difference between the totals for the two payments, he will give that amount to your team if he wins the lottery. So, like I said, a lot going on. So he's playing the lottery. He can either take a lump sum one-time payment of 51% of the jackpot and invest it, or he can get payments spread out over 20 years. So part A, if Mr. Hanks wins the lottery, and takes the payment over time, the amount he will receive from each year form a geometric sequence. What is the first term? What is the multiplier? Write an equation to represent the terms of this sequence. All right, so let me go back to my screen. So again, what is the first term? So the first term here would be 1,500,000 because that's what it tells you he would get in that first payment. And it also says that the lottery commission is going to increase the amount they pay by 5% each year. So going back to kind of before, so he's going to get 100% plus 5%. So basically it's 105% every year, which tells us that our multiplier R is going to be 1.05. And I should have written it here to be consistent. The notation for the first term, remember, is T of 1. So T of 1 is the same thing as the first term. So that tells us that our equation then, T of n, again, we could find the 0th term and write our equation this way, but that's more work. We already know the first term. The first term is almost always given to you. So 1,500,000 times 1.05 to the power of n minus 1. So that's going to be our equation here. Again, I'll show you what, if we had worked backwards to find the 0th term, we would have taken 1,500,000 and we would have divided by 1.05. And this would be what we would want for our first term or our 0th term. And so it's just not nearly as friendly of a number. So I'm going to write it this way. Part B says, if he takes the payments over time, how much will he receive in the 20th year? So B is T of 20. So for T of 20, we're going to take 20 and plug it in for our exponent here. So 1,500,000 times 1.05 to the power of 20 minus 1. And you can type it into your calculator like that, or you can type it in with an exponent of 19. 20 minus 1 is going to be 19. Either way, so 1,500,000 times 1.05 to the power of 19. So this tells us that his 20th payment is going to be $3,790,425.29. Remember, with money, you always want to round to 2 decimal places. And part C says when you add the terms of this sequence to determine the total over 20 years, you are getting the series. So what that looks like. So again, he gets this on the first year, then the second year he multiplies by 1.05 and then another 1.05. This ends up being, for the series here, 1,500,000 plus 1,500,000 times 1.05 plus 1,500,000 times 1.05 squared plus all the way until he gets down to the last term, which is to the 19th power. And we could calculate what these are. So again, remember this one, when you plug in 1, the exponent, this term goes away. When you plug in 2, 2 minus 1 is 1. So this is the first term, second term, third term, and then this is the 20th term. So the exponents all go down by 1 here from what term number they are. So as of now, we do not have a way to calculate that. That's kind of our goal by the end of today, is to be able to add this without actually having to type all of that into your calculator, because that's not very much fun. And we can't use our shortcut because this is not arithmetic. It's not growing like in stair-like fashion. So we're going to do problems 83 through 85 kind of all together. The way the book, it just breaks them apart. So we'll do it together. And I'm going to want a little bit more space. So we're going to, before we go back to this lottery problem, or before we try to solve that, we're going to go back to the first problem we did. And they write out in the book, if you look in the book, it says 2 plus 10 plus 50 plus 250. It's from that first problem we did today. So S of 6. So that means the sum of the first 6 terms. And they also on this told us that T of n is equal to 2 times 5 to the power of n minus 1. All of this is written in your book. I'm just copying it down from the book. So our goal is to add this together. Which, yes, we could type all these into our calculator, and it's not hard because there's only 6 terms and they're not very big numbers. But ideally, we want to be able to do this without having to add each one every time. So the first thing we're going to do is we're going to multiply by the multiplier. So in this equation, our multiplier is 5. So we're going to multiply both sides of this whole thing by 5. So 5 times S of 6. If I multiply 2 times 5, I get 10. If I multiply 10 times 5, I get 50. 50 times 5 is 250. 250 times 5 is 1250. 1250 times 5 is 6250. 6250 times 5 is 31,250. So I just multiplied by the multiplier. And now what I'm going to do is I'm going to subtract the original S of 6. So S of 6 is 2 plus 10 plus 50 plus 250 plus 1250 plus 6250. So I multiplied by the multiplier, and now I'm subtracting the original. So if I had 5 of these and I subtract one of them, I now have 4 times S of 6. And the reason this kind of works nicely, we're subtracting. So 10 minus 10 goes away, 50 minus 50, 250, 1250, 6250. Those all zero out when you subtract them here. So this becomes 31,250 minus 2. So 4S of 6 is 31,248. If I divide by 4, I get that S of 6 is 7,812. Okay, so again, we could have just added these. These aren't too hard. The reason we're doing this, that was just the sum of the first 6 numbers. But say we wanted to find S of n, the sum of the first n numbers. That would be 2 plus 10 plus 50 plus 250 plus ... all the way to the last term of 2 times 5 to the power of n minus 1. Okay, so if I follow this same method here, if I want to find the sum of the first n numbers, remember I multiplied by the multiplier. So 5 times S of n is going to be 10 plus 50 plus 250 plus 1250 plus ... This last one would be 5 times 2 times 5 to the power of n minus 1. Again, I multiplied each single term by 5. The reason it's 5 is the multiplier. And now I want to subtract the original again. So I'm going to subtract S of n. So 2 plus 10 plus 50 plus 250 plus all the way to 2 times 5 to the power of n minus 1. So by subtracting here, this is 4 times S of n. Think of this like x. 5x minus x would be 4x. When we subtract 10 minus 10, 50 minus 50, 250, all of these are going to, and then even this term right here, this 2 times 5 to the power of n minus 1, that's going to cross out with that term right before it. So we're going to be left with negative 2 plus 5 times 2 times 5 to the power of n minus 1. And I divide by 4 again. So S of n is negative 2 plus 5 times 2 times 5 to the power of n minus 1, all divided by 4. So if I just focus right here on this part, if I multiply another 5, so if I do 5 times 2 times 5, we know order of operation or order doesn't matter with multiplication. I could, if this is all being multiplied together, it doesn't matter what order I put it in. Here I have n minus 1 5s being multiplied together. But I'm multiplying by another 5 right here. So this part that I kind of put in that box there, everything else is going to stay the same, is going to be 2 times 5 to the power of n. Remember, this 5 to the power of n minus 1, that's how many 5s we're multiplying together. But I have one more right here, so that makes the minus 1 go away. If I rearrange this, it's 2, not 0.5. Oh, that was terrible. 2 times 5 to the power of n minus 2, all divided by 4. So that's the sum of the first n terms of a geometric sequence, or in this case, it would be a series. So if we think about what each of these numbers mean, so the sum of a geometric series here then, and we'll get this kind of in some notes in a little bit. S of n equals, so this 2, if we go back and look at the original problem, this 2 is our first term. So it's the first term times the 5 was our multiplier. And then a minus our first term. And 4, the 4 is a little bit tricky. Where the 4 came from was right here. 5 minus 1, remember our multiplier was 5. So that 4 is our multiplier minus 1. And it's always minus 1. So if I write this in math notation, not using the words, our first term is t of 1 times our multiplier is r. Oh, that needs to be the power of n, I'm sorry. Or multiplier to the power of n, I forget that part. So t of 1 times r to the power of n minus t of 1 all divided by r minus 1. I often leave it in words. I think that makes it a little bit easier, but this is the same thing. All right. So that was 83 to 85. So 10-86. It says Antonio is working with a new geometric series generated by the equation t of n equals 30 times 1.2 to the power of n minus 1. His sister challenges him to compute the sum of the first 37 terms. Okay, so if we want to find the sum of the first 37 terms, we're looking for S of 37. So the few things we need to know here, so we need to know T of 1. That's our first term, 30. We need to know R. R is our multiplier, which is 1.2. And we need to know N. N is the number of terms. So N here is 37. And then we can just plug it in there. So S of 37 equals the first term 30 times the multiplier 1.02 to the power of 37 minus our first term is 30, all divided by 1.2 minus 1. So you can plug this into your calculator. If you want to plug it in one step, you have to be very careful with your parentheses. I don't recommend doing it in one step. Most people tend to make mistakes when they do it that way, but you are welcome to try to do it that way. But I would do your numerator, personally, the numerator and denominator separately. Because if you just plug it in like this, I want to show you what not to do. Oops. And then if you just do divided by 1.2 minus 1, you're going to get the wrong answer. You're going to get like 36. Well, we know if we're adding 30 as our first term and we're adding 37 terms, it's going to be a much larger number than 36. So you would have to use parentheses around the whole numerator on the calculator and the whole denominator. Or you can just do them separately. 30 times 1.02 to the power of 37. Make sure you go over. And then divided by 0.2. I did something wrong. Oh, it's not 1.02. That's where I'm wrong. It's just 1.2. I don't know where I got that 0 from. Don't do that. I don't know what's going on with my whiteout also. 1.2 to the power of 37. That'll make a difference. So our numerator is 25,486.8675, and divided by our denominator is 0.2. So we get 127,434. I'll just, yes, there's a decimal if you want to include it. So the sum of the first 37 terms is approximately this. All right. So that was kind of a lot, but we're going to kind of just, let me look at 94 and 95 because I do want to formalize these notes a little bit for you. Does anyone need that still? Okay. So let's see, geometric series. So just to kind of start us out here, a geometric sequence has a common ratio R and is created by repeated multiplication. So an example just of a geometric sequence would be like 8, 16, 32, ... So the equation here is T of n equals 8 times, and then we want to figure out what R is. Remember, so to figure out what R is, our multiplier or the common ratio, you divide the terms. 16 divided by 8 gives us 2. So that's 8 times 2 to the power of n minus 1. Or you can write it the old way. T of n equals 4 times 2 to the power of n, where this is the 0th term, and then that's R. Here we have the first term, and we also have R. So you get to choose what way you want to do it. I will most commonly do it this way, but these are the same thing. So let's see. I want to look at the notation I used there. Okay. I just want to make sure I'm using the same notation on the last problem. So for a finite geometric series. So finite means it ends. We're going to look at some problems tomorrow that are going to be infinite. So for a finite geometric series, S of n is equal to T of 1 times R to the n minus T of 1 all divided by R minus 1. This can be written a few different ways, just kind of as a heads up. If you see it, you can simplify these a little bit differently. So we'll just use that same example. Find the sum of the first 16 terms. So 8 plus 16 plus 32 plus ... And we want 16 terms. So we need to know t of 1, which we already know is 8. We need to know r, the multiplier is 2, and then n is how many terms we have, which is going to be 16. So here s of 16 is equal to 8 times 2 to the power of 16 minus 8 divided by 2 minus 1. So again, if you put this into your calculator as one step, you need parentheses over the whole numerator divided by the whole denominator. I personally just do my numerator and denominator separately. So 8 times 2 to the power of 16 minus 8, I get 524,280, all divided by 1, which we know is just 524,280. But again, if you want to type this into your calculator in one step, it would be 8 times 2 to the power of 16 minus 8 in parentheses divided by 2 minus 1 in another set of parentheses. You're going to get the same thing. Okay, and then let's just do, we'll do part of 94 and 95. I just want to do a couple. So here, 10-94, part A. So it says determine if these are arithmetic, geometric, or something else, and calculate the sum. So part A is like this. The sum from t equals 0 to 15 of 5 times 2 to the power of t. So this one is a little bit weird, and I probably should have picked a different one. But this is going to be geometric because it's in this form. So here, the first term, if I were to write this out, is when I plug in 0, not when I plug in 1, because this one goes from 0 to 15. So think about if I plug in, what this means if I write it out, this would be the same as 5 times 2 to the 0 plus 5 times 2 to the 1 plus 5 times 2 to the 3 plus all the way to 5 times 2 to the 15. Again, I plug in 0, 1, 2, 3, 4, 5, all the way until I get to 15. So for this problem, we still need to know these same 3 pieces of information. We need to know the first term. We need to know what our multiplier is, and we need to know what n is. So here n is still 16. It's not 15 because we go 0, we're counting this 0. This is our first term, second term, third term, fourth term, all the way, and this will be our 16th term. This right here is t of 1. They used a t here, and that makes it a little bit confusing. I just picked the one from the book. I should not have done that. But our first term here is 5. And our multiplier is 2. So we just plug it in. So this would be 5 times 2 to the power of 16 minus 5, all divided by 2 minus 1. which gives us 327,675. All right. We're gonna stop there. I was gonna make one. The rest of them in the book are arithmetic. That's not true. Part E is geometric, but it's not a very good looking one. I don't like this example. I probably should have skipped, not even done part A, but that's okay. We will get more practice with geometric tomorrow. Just kind of a heads up for where we are. I don't know if I should end on that one. It's really bugging me. I don't like it. Tomorrow we're doing more geometric and then also combinations and permutations, which hopefully those words sound familiar. They were at the end of Math 2, which I know was online last year. So you probably didn't get very much out of them. So I know we need to review some of that stuff because for where we're going from here. Please ask questions. This, like I said, I know is a little confusing. Hopefully this part made sense. What we did today, all of this was to kind of determine how to come up with this formula for the sum of a geometric series. And we just had to remind ourselves what it actually meant for like a geometric series and a geometric sequence. But your homework is still 97 to 103. And if you have questions on it, please bring them tomorrow or email me. Look at the homework help, look at the solutions and see if they make sense. But you